Imagine trying to build a global rail network or share a chemical formula when every country uses a different ruler and a different scale. Prior to the modern era, the lack of a shared scientific language made comparing data across borders nearly impossible. Early attempts to standardize gave us the CGS system. This scheme broke physical quantities down using the centimeter for length, the gram for mass, and the second for time. Meanwhile, the British relied on the FPS system, feet, pounds, and seconds. A reading of pounds and ounces on a dial like this meant nothing to a French engineer running calculations in grams. As early industrial machinery and high-precision instruments grew more complex, scientists leaned toward the MKS system, meter, kilogram, and second. It offered a scale better suited for major engineering. But running three separate systems side by side created a mathematical wall. Sharing blueprints or trading precision parts required constant, error-prone translations between competing local standards. The scientific community needed a single vocabulary. The eventual adoption of the International System of Units, or SI, solved this by creating an internationally accepted reference standard. A measurement taken in Paris was finally mathematically identical to one taken in Tokyo. To make a universal system work, you need absolute physical reference points. For decades, global accuracy relied on specific, highly guarded prototypes, like this platinum iridium cylinder used to define the exact mass of 1 kilogram. This table illustrates the core realization of the SI system. You don't need a unique unit for every phenomenon in nature. You only need 7 base quantities. The first 3 form the bedrock of mechanics: length measured in meters, mass in kilograms, and time in seconds. To cover the rest of physics and chemistry, they added 4 more: the ampere for electric current, the Kelvin for thermodynamic temperature, the mole for the amount of a substance, and the candela for luminous intensity. Because the SI standard relies on a decimal system, converting these measurements is simple. Moving from a millimeter to a kilometer is just a matter of shifting a decimal point. These 7 units give us a complete alphabet. Combine them properly, and you can spell out any physical measurement we know how to make. There is a slight exception to these 7 base units. When you measure an angle, you aren't measuring an amount of matter or energy. You are measuring geometry. For flat, 2-dimensional space, we use the plane angle. Its unit is the radian, which compares the curve of an arc to the straight line of its radius. The radian is defined by a simple ratio: the arc length divided by the radius. If you pull that concept into 3 dimensions, you get the solid angle, measured in steradians. Instead of an arc on a flat circle, you are looking at a cone extending outward to the surface of a sphere. The steradian is the ratio of that intercepted surface area divided by the square of the radius. Because both of these units are just dividing a length by a length or an area by an area, the physical units cancel out. They act as dimensionless quantities. Once you have these base units and geometric angles, you can scale up. Tracking an object like a satellite in orbit requires us to calculate complex metrics like speed, acceleration, and force simultaneously. We do this using derived units. Instead of inventing entirely new measurements from scratch, we multiply or divide our existing base units to express new physical realities. This visualization shows how a unit of force, the Newton, is constructed. It's derived exactly from the base units for mass and acceleration: 1 kilogram multiplied by a meter divided by seconds squared. Science replaced a chaotic web of competing local standards with a rigid structure: exactly 7 base units plus 2 dimensionless units for measuring geometry, and this structure updates itself. Groups like the International Bureau of Weights and Measures routinely revise the precise definitions of these base units to ensure they match our most advanced measuring techniques. By agreeing on this shared vocabulary, researchers anywhere on the planet can verify each other's work, giving us a reliable way to measure and understand the physical universe.